So number 8, quite a straightforward factual one. Friction is a force which opposes motion, i.e. it causes moving objects to slow down and keeps stationary objects at rest, or attempts to keep. You think about trying to move a big wardrobe, you can get enough force to cause it to move, but you're having to oppose the friction in the first place. Other things that are worthwhile knowing about friction though. Friction increases with increasing speed. Okay, so, and within friction would include drag forces increase with increasing speed as well, and that's quite important. And last one, energy change. Friction converts kinetic energy into heat and possibly sound, but heat is the dominant one there. And then in number 9, we've got to use that knowledge along with Newton's first and second law to describe and explain terminal velocity. So I've got some diagrams here that I've copied. I'm going to label some of the points. Kind of key points of change. I'm just looking for where this one flattens out, probably around about there. Okay, and I'll explain why in a wee second, but that's what's going on during AB, BC, CD, and DE. So what's happening during AB? Well, as soon as the parachutist leaves the airplane, he or she experiences a downwards unbalanced force, their weight. Now, just at that instant as they've stepped out, and we're ignoring sideways motion here, then there won't actually be any air resistance just as you start to move, just like we dealt with in the rocket. But the weight causes them to speed up, which in turn, because air resistance increases with increasing speed, then the air resistance is going to increase. So between A and B, it's accelerating downwards, right? They're accelerating downwards, but their acceleration will decrease. It's a decreasing acceleration, and we can see that from the graph because the graph is getting less steep. Okay, so this is the only kind of non-constant acceleration that we'll look at in the higher course. Oops. So the acceleration decreases due to a smaller unbalanced force. So we've used Newton's second law, basically, that we've got this idea that acceleration decreases due to smaller unbalanced force. So we'll put in brackets fun equals ma. Between B and C, the parachutist falls with constant velocity. Because the air resistance now balances the weight. And try and use a technical term. If you just say equals the weight, then you'd have to be clear that they're in opposite directions. So the air resistance now balances the weight. There is no unbalanced force. So by Newton's first law, velocity is constant. Now at point C, they open the parachute. The open parachute has a larger surface area, so it experiences more air resistance. Now remember, the air resistance is acting up the way. The weight's not changed, it's still acting down the way. So the unbalanced force is now upwards. Now this doesn't mean that the parachutist moves upwards, because they're already moving with probably quite significant downwards velocity. So when you apply an upwards force to that downward velocity, it's not going to instantly change to moving upwards. The upwards force, which causes an upwards acceleration, is going to subtract away from the downwards velocity, but that will take time. So the unbalanced force is now upwards. This causes the downwards velocity to decrease. Okay, so we've got a downwards deceleration, if you want to call it that. It's the same idea as an upwards acceleration, remember. So this causes the downwards velocity to decrease, meaning the air resistance also decreases. And this downwards deceleration will decrease as well. So the unbalanced force decreases and the upwards acceleration or downwards deceleration decreases. So that's why it's not a straight line again. Okay, it's going to flatten out more gradually. Now, why do people often think that opening a parachute does cause you to fly upwards? Well, it's usually to do with perspective of who's doing the filming. If you've got two people in free fall, one with a camera watching the other one, and the other one opens their parachute, the camera person, unless they've somehow got them linked together, is going to have a wee split second where that person is slowing down dramatically. They do slow down very quickly, the line's quite steep at that point. And so they're going to continue to fall at the speed they were falling a wee second ago. And so even if they open their parachute within a split second, the other person is going to slow down much quicker. And so from their perspective, they're going to end up way above them. right? But it's not, they're both still continuing to fall down. It's that the camera person hasn't opened their parachute as quickly, so they're falling down a wee bit more quickly. And then DE, we reach the exact same idea as we did in BC, back to constant velocity, right? Because we were talking a second ago about the air resistance decreasing between C and D. So the air resistance has decreased, and it now balances the weight again. And remember, the weight has been constant throughout. So basically, the amount of air resistance for the parachutist in free fall without the parachute open is the same as the amount with the parachute open. But because of the much bigger shape, you can get that in a much lower velocity. It's the same amount of air resistance. So the air resistance now balances the weight, and by Newton's first law, velocity is constant again. And then at the very end, they hit the ground and you get a sudden stop from a different force. But you're not usually interested in that bit, or we'll actually look at that later on in the unit, those sorts of ideas. Now, all these ideas that we've talked about here can apply when you are accelerating a car, for instance. Okay, if you think about it, if you press the accelerator, the car starts to get faster, but then the air resistance starts to increase, so the car reaches a terminal velocity. And that's what's so important about designing cars. So the engine force, you want that to be as large as possible if you want the car to go faster, but you also want the air resistance forces to be smaller for a given speed. So that's why you have to make them streamlined as well. Okay, 11 and 12, some simple factual stuff for 11, and then we'll look at a worked example for 12. So, resultant of a number of forces, and usually we'll look at 2, but it could be more, is the same as the single force which would have the same effect. And resultant and unbalanced force both mean the same thing. We'll look at a worked example. A packing case is pulled by 2 forces at right angles to each other, as shown below. What is the resultant force? And there are 2 ways of doing it. You can do it by Pythagoras in these cases, because it's at right angles, or you can do it by scale drawing. If they're not at right angles, we'll look at other ways of doing it, but scale drawing may be easier in some cases, but most students prefer not to do scale drawing, so I'll look at ways of doing it without scale drawing. So in terms of Pythagoras, the first thing we've got to watch here is that these 2 forces act from the same point. Now when we are adding vectors, remember we've got this idea that you've always got to add nose to tail. So we have to redraw these vectors. So we'll have 100 Newton, and then we have to start the other one. Now I'll get the same answer if I picked the 50 first, but they're at right angles to each other. And because I can use, in fact I'll not use colours because you generally find it a wee bit harder. There's no reason to expect that this is actually exactly left to right, in fact it probably wouldn't be, but that is a resultant vector there. So how can we work out the size of that? Well, it's quite straightforward, bit of Pythagoras. So A is square root 1,500 equals 1, 1, 2 newtons. And for the angle, I'm going to call it x. You can call it theta quite often in physics, but tan x equals opposite over adjacent. Make sure you're getting them the right way around. So where I've picked x, 50 is the opposite. So x is tan to minus 1 of 0.5 is 27 degrees. Now here I've not got any north, east, south defined. Okay, so all I can do is be clear about that x is beside the 100 Newton force. So I write my final answer as the resultant force is 112 newtons at 27 degrees to the 100 Newton force. Now, having learnt in the previous two learning outcomes about how to take forces at right angles to them and find the resultant, the next bit is the opposite. Quite often you do this in maths, learn how to put things into brackets, learn how to take them out of brackets, and often it's important that you can work both ways. So in this sort of stuff, we're going to look at the idea of how to find what we call components of a vector. And this would be, say, taking a vector. So for example, 100 newtons, it can be any vector, it could be a velocity at 30 degrees to the horizontal. And what we want to do is to find, well, how much of that is horizontal and how much of it is vertical. So it's like we are given the resultant and the angle, or the resultant including the angle, and you're being asked to find the two components at right angles to each other. Now, it doesn't have to be horizontal and vertical, but quite often that's really useful. When we return to looking at projectiles, for instance, in the higher course, then we'll take this sort of idea, and that's how we take motion in 2 dimensions and we split it into 2 one-dimensional motions, which is what we've dealt with up to now. Okay, so we can take more complicated situations and simplify them into one-dimensional motion. So this is fairly straightforward, but once again using trig, so if I call this H and call this V for horizontal and vertical components, then I can use simple trig. So I've got the hypotenuse as 100. So if I look at the horizontal first of all, to get H, then it's adjacent to the 30 degree angle. So I'm going to look at cos. Cos 30 degrees is adjacent over hypotenuse, which is the H that I'm trying to work out, divided by 100. So multiplying both sides by 100, I get H equals 100 times cos 30 degrees. 86.6 newtons. It is a force. You're taking a force and working out how much of it acts in each of these 2 directions. And then the same idea for the vertical component. But it's based on the opposite. The V is opposite the 30 degrees here. So sine 30 is opposite over hypotenuse, which is the V we're trying to work out, over 100. So V is 100 sine 30 is 50 newtons. So these are the 2 components, as we call them, of that vector, that original. And it could be quite easy to work out, you're just multiplying the 2 components by sine 30 and cos 30 to work out which one's which. You just got to go back and say which one's adjacent. That uses the cos component. So the H here is adjacent to the 30, so it uses the cos component. The V is opposite. Now here's a useful worked example based on that, where you've got a pair of forces. Okay, now notice these are not got 90 degrees between them, so you can't go and do the Pythagoras that we did earlier and finding the resultant. But to find the resultant of these, what we can actually do is find the components So for instance, we can look at the horizontal component of that top force there and the horizontal component of the bottom force there, and you can see they both act in the same direction. And we can look at the vertical component of that top one there, which acts up that way, and the vertical component of that one there. Oh, they're not actually horizontal and vertical here, to be clear, it's not really that well defined, but you can certainly see that those two act in opposite directions, where the two green ones act in the same direction. So those components are, the green one is the 4 times 10 to the 4, which was actually included in the diagram but is mentioned in the text. And notice it says the angle between the ropes is 60 degrees, but we've split that into two 30s. So this is the adjacent component because it's right beside the 30, so that's cos 30. So is that one. So those two are the exact same and they both add up, they're both going in the same direction. The yellow component, well, we actually don't need to work it out, but just to be complete, it's the sine component. And you've got the exact same force in this case, but they're cancelling out anyway. So the resultant force using these components would be 2 times 4 times 10 to the 4 times cos 30. And if you calculate all that, you get 6.9 times 10 to the 4 newtons, and because it's a force we need to give it direction. We haven't defined up or down or north, east or south, anything like that. Right, so we'll put, sorry, not across, along the centre line. And the last learning outcome, 14, is looking at the idea of the weight of the object on a slope. So if you have an object of mass m, its weight is mg, which acts straight down. But in actual fact, what's much more useful for us to be able to study are the two components of that weight. So just taking the same ideas that we're just talking about, we can talk about components which go that way, directly into the slope, and components which go that way, down the slope. Now if we define the angle of this slope as being theta, then that angle in there, it's hard to draw, is also theta, because the way it acts straight down. Okay, so that would be a right angle in there, which means that angle there would be 90 minus theta, and the angle between the slope and this, we said that's directly into the slope, and by that we meant at 90 degrees. So that's 90 minus theta, and these two add up to 90, so that one in there must be theta. Now you'll not be asked to derive that, but you do need to know these two components, and they're not given in the formula sheet. Never been that clear why. But this component is mg cos theta. Can you see it's adjacent to the theta there? And the yellow component is the mg sin theta component. So we're just taking that weight mg and resolving it. And what happens in reality with an object on a slope is that the component that goes into the slope is simply balanced by what we call contact forces with the slope, in the same way that when you stand on the floor pushes back with the same forces. You're getting pulled down. So that would happen here. So in the real world, that mg cos theta component just gets cancelled out by a contact force. So basically it doesn't really affect the motion. It's the mg sin theta component which will control your one-dimensional motion up and down the slope. So when something's on a slope, it's actually the mg sin theta component which is most useful to the plane. So it's known as being parallel to the plane or down the plane. So the weight down the slope or parallel is mg sin theta. And let's say you're not given that, but you will be expected to know it. the weight into the slope, which isn't so useful to be honest, would be mg cos theta. Now to help you remember the sine theta component, if you think about if this slope was flat, i.e. theta was 0, then the weight down the slope would be 0. And that might help you remember if you know that sine theta is 0, cos theta isn't, cos theta is 1. That might help you remember which one is a parallel component. So that's a kind of background theory, and then we'll look at a worked example of that. So here's our worked example. Wooden block of mass 2 kilograms placed on the slope at 30 degrees. Force of friction acts 4 newtons acts up the slope. The block slides down the slope a distance of 3 meters. Calculate the acceleration of the block on the slope. Calculate the speed of the block at the bottom of the slope. So this is going to give us a wee bit of revision of some stuff that we've done previously. So we're going to consider a free body diagram down the slope, or up and down the slope, for our object. We know from what we've just been doing there that the weight down the slope will be mg sine theta, and we know there's a force of 4 newtons acting up the slope. So that's what a free body diagram looks like. We want to work out that mg sine theta before we can go any further. So we've got everything we need for that. Is 2 times 9.8 times sine 30, which is 9.8 newtons. So the unbalanced force, remember the whole point of our free body diagrams, is 9.8 minus 4 equals 5.8 newtons. And then we know Fun equals MA, so 5.8 equals 2 times A equals 5.8 divided by 2 equals 2.9 meters per second squared. That's our answer to part A. And then for part B, calculate the speed of the block at the bottom of the slope. I'm just checking to actually make it that clear, but it should have made it clear that the block started from rest. Part B, it's going to be a u-vast problem. It's accelerating down the slope. We know u is 0. Oops. Meters per second. V is what we've been asked. A we've just worked out is 2.9. Taking that positive to be down the slope in this example, because everything's moving down the slope. We can be consistent. It was 3 meters was S, and that's enough to solve for V. So we can do V squared equals U squared plus 2AS. 0 squared, remember, is 0. So that gives us that V squared is 17.4. V's square root of 17.4 equals 4.2 meters per second.